Congratulations, you made it to the final learning video in our astronomy section. And it's a big one. It's all about the universe. Edwin Hubble is credited with looking up into the sky and noticing that something they had called the Andromeda Nebula was actually another galaxy. He was the one that determined there are other galaxies out there besides the Milky Way. Not only did he figure out that there were other galaxies, he also figured out, one, that they're all moving away from us using the redshift of light that we've talked about before, and two, that the farther away the galaxy is, the faster it's moving away. So those were really interesting things. And then for me, I think the best part is that he did this all up in Mount Wilson, right above Pasadena. So how can all galaxies be moving away from us regardless of where we look? Are we in the center? No. But the whole universe must be expanding. The size of the universe is not fixed. And prior to this time, everyone believed that the universe was fixed in its size. Even Einstein, who made an exception in one of his equations because he thought the universe was fixed. Later on, he actually met Hubble, went up to Mount Wilson, and said it was one of the biggest mistakes of his entire career to not realize that the universe was expanding. But nobody holds that against Einstein. Here's a little cartoon showing the universe starting with a Big Bang and then expanding over time until today at about 13.7 billion years. And the number that we come up with, 13.7 billion, is from taking the speed and direction of the galaxies, reversing them, and they all seem to come to a point at 13.7 billion years in the past. So this theory suggests that the universe began with a big cataclysmic explosion 13.7 billion years ago. Very commonly, you'll see the raisin bread analogy for the expansion of the universe. So let's look at this diagram on the left. Here's some dough, and these raisins are in the dough, and let's say that we live on this raisin right here. This is our galaxy. And there's a galaxy that's 2 centimeters away, and there's another galaxy that's 5 centimeters away. So after some time, the entire bread rises, the dough rises, and now we've tripled the distance between us and other galaxies. So 2 times 3 is 6. 5 times 3 is 15. And so now everything is farther apart from everything else. Now pay attention to how much the distance has changed. Over here on the left, this galaxy was 3 centimeters farther from us than this one. Over here, this galaxy is now 9 centimeters farther from us than this one. And so what that does is that makes the speed of this going away from us faster. It looks like this one is moving away faster. So this is an analogy for the expanding universe and the fact that the farther the galaxy is, the faster it's moving away from us. So the Big Bang marks the inception of the universe. All matter is moving outwards. However, not all matter is moving outwards at the same rate. Remember that when we look into space, we're looking into the past. If we look at something that's 1 million light years away, then we're really looking at something that's 1 million years old. That light is 1 million years old, and who knows what's going on with that object right now. So when we look into space, we're looking into the past. And that's how we can look back towards earlier times. And what we've noticed is kind of depicted in this cartoon. So here's the expanding universe, here's time, the present is up here, the past is down here. The more spread out things are in this diagram, the faster they're expanding. So astronomers believe that after the Big Bang, there was a period of rapid expansion, and then there was this slower period of time when the gravitational pull of the galaxies were acting on each other and sort of slowing down the expansion. However, now, in present time, we see that things are moving faster and faster away from each other. And this necessitates something called dark energy, which we'll talk about in just a moment. Here's an interesting diagram showing how the temperature of the universe has changed over time. And this is a very unusual scale because we have a logarithmic scale at the bottom and a logarithmic scale on the left. So this is temperature, and this is time. And so 10 to the minus 43 seconds is, as you might imagine, a fraction of a second, as are all of these things here. All of this time right here is all happening in less than a second. Astronomers have figured out that these various things form at these various temperatures. And then 10 to the 7 seconds into the formation of the universe, which is a million seconds, we have our first atoms forming, and then eventually galaxies, stars, and here we are today. So there are two possible fates of the universe. One is that it can keep expanding forever, and the other one is that it will slow down and eventually gravitationally pull itself back together, and this is sometimes called the Big Crunch. The expansion idea has three possible scenarios, and all of these are shown here. This is another diagram from your textbook. So here's the past, here's the future. This star represents the beginning of the universe, and the yellow box here, I guess you call it a box, that's where we are today. So today we have a universe at this size. If, as I said, the gravitational energy is strong enough and pulls everything back together, then the expansion will slow down, decelerate, everything will come back together in the Big Crunch. These three scenarios all have the universe expanding, but just at different rates. This one has the universe expanding at a slightly slower rate over time. The coasting universe has it expanding at a constant rate. And then this one over here has it expanding at a faster and faster rate. What's going to decide which of these things happen? There's something called the critical density. If our universe's average density is more than this critical density, then we're going to contract. That means that we're so dense that mass is going to pull everything back together. If the average density of the universe is less than the critical density, then things are going to keep expanding. However, there are two other things we need to consider: dark matter and dark energy. So dark matter is material that's not visible, but it exerts a gravitational force. And this became necessary to postulate because when we look at, for example, the Milky Way galaxy, and scientists calculate all the mass of all the stars and all the gravitational pulls, our galaxy should not be held together. There's missing mass. There's a missing source of gravitational pull. And so that's dark matter. And so ultimately, dark matter helps to slow the expansion of the universe because it's got a gravitational pull. Then there came along something called dark energy. And this is the opposite of dark matter. This actually helps speed up the expansion. Dark energy has not been conclusively found, but it's necessary to explain that accelerated expansion that I just mentioned in the more recent history of the universe. So today, scientists believe that our universe is only about 5% of what we would consider ordinary matter, stars, everything that emits light. And then there's 27% dark matter and 68% dark energy. Here's a slide that I like because it shows how things have changed in just a few decades. Back in the 1970s, there was ordinary visible matter, and the rest was ordinary dark matter. And this is the composition of the universe. And that ordinary dark matter, as I mentioned, exerted a gravitational pull, but scientists believed it was maybe like protons and electrons, but didn't give off any wavelength. By the 80s, they decided that no, this is a material that we've never seen before. We don't have any of it on Earth. And so they kind of renamed it as exotic. And we here have the ordinary dark matter, and then our visible matter is just this little slice. Then by the 90s, dark energy came into the picture, and now we have dark energy, exotic dark matter, regular dark matter, and then you can see that the visible universe that we know of is becoming a smaller and smaller slice of the pie. Congratulations again on making it through astronomy. We have an exam coming up, and then we're going to move on to a totally new topic, meteorology.